We're going to take a little look at what the notation means for the Riemann sums in the definite integral. So you may have seen something like this. The limit as n approaches infinity of the sum k equals 1 to n of perhaps something like this, f of a plus k delta x, and then multiply it again by delta x. So what does that mean? This is actually a shorthand notation for the right endpoint. Up here is the right endpoint approximation, and once you take the limit, you get the exact value for the area under the curve. So basically what this kind of looks like on a graph would be something like this. Suppose you've got a function and it's defined between two x values, let's say a and b, and you want to find the area under the curve. So maybe the function looks like this. What this is saying is that we're going to start at f of a plus k is 1 means a plus delta x. So basically what that means is you've got like an x value here. You can call that like x1 or something like that. And the distance between them, this is a fixed distance, so no matter how many x values you look at, that x value, that distance is always the same. So delta x is always the same through all of them. So basically, since it says a plus k delta x, and k is starting with 1, that means that the first one that we're going to plug in is this value right here. This is a plus delta x gets us to this point right here, okay? And so what we're going to do, f of that is this height right here. It says f of that value, right? So again, if you were to write this out in longhand, what would it look like? It would look like f of a plus k is 1, that's the first one you plug in, f of a plus delta x, and then multiplied by delta x. So a plus delta x is this value right here. F of it is this, so this is a height, and then we're multiplying that by delta x. So basically, if you kind of want to imagine what that looks like, it's this rectangle right here. So the area of this rectangle is this quantity right here. Then when k iterates to 2, then what are you looking at? Then you're looking at f of a plus k is 2 now, so 2 delta x, again multiplied by delta x. Okay, so now what? Well, that's a. Now we're adding 2 delta x's to it, so now we're here, and we're again taking f of that value, right? So that means we're going to plug that into the function. That's a height. F of this value is a height, and then delta x there is the width. That's this delta x is the same width for all of them again, so that would be like the second approximating rectangle. And it just keeps going like that until you reach the nth rectangle. The nth rectangle will invariably be the last one. Okay, so the last rectangle here, that would be when we've reached n, and the last rectangle, right end point, would look like this. Okay, so this was the last one once we reached n. Now what this is doing, that's taking the number of rectangles as it goes to infinity. So what that does is it basically lets delta x shrink smaller and smaller, gives us more and more rectangles, and so we get a better and better approximation. If you let the number of rectangles go to infinity, well, basically you would get the exact area under the curve, and then that quantity, this whole thing put together, is the definite integral. That would be this value here, integral from a to b of f of x dx. Okay, now this is the right endpoint approximation because we started at 1. If we were going to do a left endpoint approximation, all we would have to do is just start this at 0 and end it at n minus 1. Because if we started it at 0, then it would be f of a, because that would be a 0. So that our first one would be the height here, and then our first rectangle would be kind of like that instead. Okay, so left endpoint approximation, start at 0 and end at n minus 1. In the limit, it doesn't matter whether you start at the right or the left endpoint, or in fact at any point in between the interval. They all give you the same value for the definite integral. So that's one notation that you might have seen. Another one that you might have seen is this, the limit as n goes to infinity of sum k equal 1, 1 second, k equal 1 to n of f of a plus, actually I think in this one is just f of x sub I and then delta x. So what is this one? Well, basically what you'd have here is they would just be numbered. So instead of like starting at maybe this one, instead of being called A, we might let me just erase it, and you might say that A is identified as the first x value. So you could call that like x naught. You could even still call it A if you wanted to. In this case, then what we would be doing is each little endpoint of a subinterval would be identified with a subscript. So like I have here. So again, if I'm doing a right endpoint approximation, I would start with 1, and so f of x1 would be this one here. The first iteration of k would be, that would become x1, and then I would still get the exact same rectangles I did with this notation up here. And then what would happen? The summation notation iterates, and we'd get to x sub 2. This would be f of x sub 2, so it'd be here. F of x sub 2 would be the height of that thing multiplied by the width delta x, and so on and so on. So basically, if you were to write this one out longhand, you would get f of x1 times delta x plus f of x2 times delta x, and so on, until you reach the last one, which would be f of xn, which again, you might call this last one xn. Okay, and so you'd get to that one, and that would be the last one, and that would give you an approximation of the area under the curve. That would be, again, a right endpoint approximation if you started at 1. If you wanted a left endpoint approximation, you could start at 0. So 0 would be the first one, your height of your rectangle would be here, and then you would end it at n minus 1. So the last one would be this one right here, the n minus 1 rectangle. That would give you a left endpoint approximation, but again, either way, it doesn't matter which approximation you use. Once you put that limit on there, they both will give you the exact same value, which is the exact area under the curve. So I hope this helped to show a little bit about what this notation is talking about. Both of these represent exactly the same thing. They both represent the definite integral. Okay?